First question is how to draw pressure, volume and temperature entropy diagram for Rankine cycle with incomplete evaporation, which is thermodynamic vapor cycle. Second question, solve one problem for Rankine cycle with incomplete evaporation with the help of steam table. Let us understand how to draw pressure, volume and temperature entropy diagram for Rankine cycle with condition incomplete evaporation. As this cycle is known as thermodynamic vapor cycle, steam is used as a working substance. If we observe the diagram, boiler, turbine, condenser and hot well are the four main components through which the steam is passing when the different processes are taking place. Now we will consider what is the initial condition of working substance. We will consider 1 kilogram of saturated water is entering inside the boiler at pressure P1, volume V1 and temperature T1. Now we will show this initial condition of the working substance. So here will be point 1 at the entrance of the boiler. Now it is at pressure P1 and volume V1. So I will show here the point 1 at pressure P1, volume V1. And if we observe this temperature entropy diagram, here is saturated liquid line and saturated vapor line. As initial condition of the working substance is saturated water, that means it is in liquid phase, we have to show this condition, that is the point 1 on the saturated liquid line. So I will show here point 1 at temperature T1. Now we will move for the processes. So process 1 to 2 is taking place inside the boiler, which is heat addition at constant temperature and pressure. Now we have to show this process. So we have to keep pressure constant, temperature constant. Now what is the effect of heat addition on other parameters, that is volume and entropy? So we know that during the heat addition process, volume is getting increased as well as entropy is also getting increased. Now if we observe the condition, there is incomplete evaporation. So what is the meaning of this incomplete evaporation? So when the heat addition process is taking place, saturated water is getting converted into dry saturated steam. But instead of this complete conversion into dry saturated steam, it is getting converted into wet steam. So we have to show point 2 in between this saturated liquid line and saturated vapor line. So in between this, that means somewhere here we have to show this. And we have to keep pressure and temperature constant. Now we will draw this line. Pressure will remain same, but its volume will getting increased. So here will be point 2 with volume V2. And now here temperature will remain constant but entropy increases. So we have to show wet steam. So I will show here point 2 with dryness fraction x2. Because point 2 is the wet steam, so it is having some dryness fraction, or we can say quality, and it is x2. Now how to calculate the heat absorbed during this process 1 to 2? For that we have to take the enthalpy difference. So what is the enthalpy at point 1? So point 1 is on the saturated liquid line, that means phase of the working substance is liquid. So we have to take H to the base F, because for liquid we will take enthalpy HF. So at point 1 I will say HF1. And what is the enthalpy at point 2? So it is wet steam, so I will say H2. Now we have to write this H2 in detail. So how to write it? So H2, that is equal to, so I will write somewhere here, H2 is equal to HF2 plus X2 HFG2. So we can write this H2 in this way, because we have to consider this dryness fraction, because at point 2 it is wet steam. Now what is the heat absorbed? That is, we have to take the difference in between the enthalpy, that is H2 minus HF1. So I will write here H2 minus HF1. So instead of H2 I will write this whole, that is equal to HF2 plus X2 HFG2 minus HF1. Now again, if we observe, this process 1 to 2 is taking place at constant pressure. That is, here P1 is equal to P2. That is, pressure at point 1 is equal to pressure at point 2. So if we observe, if we take the reference of the steam table, then at constant pressure HF1 is equal to HF2. So in this formula, if we observe, HF1 is equal to HF2 and this HF1 is having minus sign, so it is getting cancelled and we can take only X2 HFG2. So this is the formula that we have to take to calculate the heat absorbed. Now we will move for the next process, that is during the this process 1 to 2 is taking place for the boiler. So here will be point 2. Now at point 2 there is the wet steam. Now this wet steam is entering inside the turbine and isentropic expansion process is taking place. Now how we can define this? Here the expansion is taking place with constant entropy. And when this entropy will remain constant, then there is no any heat added and no any heat rejected. So we will show process 2 to 3 is taking place inside this turbine. So what is the effect of expansion on the other parameters, that is for temperature, pressure and volume? So here because of expansion we know that pressure decreases, and as pressure decreases temperature also decreases and volume increases. So we have to show this process 2 to 3. So decrease in pressure, at the same time increase in volume. So here is the volume V3 and we have to show pressure P3, and entropy will remain constant and we have to show decrease in temperature. So here will be 0.3, then temperature T3, and here entropy S2 is equal to S3, and at point 1 here the entropy will be S1. So this process is getting completed. Now again we will move for the process 3 to 4, which is taking place inside the condenser, where the heat rejection at constant temperature and pressure. So again we have to show pressure constant, temperature constant, and what is the effect of cooling on the other parameters, that is entropy and volume. So due to cooling, entropy decreases and here volume also decreases. Now this cooling process is taking place until this wet steam is getting converted into saturated water. So this is the condition. So we have to show this 0.4 on the saturated liquid line. So we have to show decrease in entropy, and I will show here this 0.4 because this will be on saturated liquid line, and here also we will show this pressure P3 is equal to P4, here will be 0.4. Now we have to calculate the heat rejected. So again for the heat rejected we have to find out the enthalpy. So what is the enthalpy at point 3? Because it is the wet steam, we will say enthalpy at point 3 will be H3. And what is the enthalpy at point 4? So at point 4 it is saturated water or saturated liquid phase. So enthalpy at point 4 is HF4. So heat rejected is equal to H3 minus HF4. Now again we will find out what is this H3. So H3 is equal to HF3 plus X3 HFG3. Now if we observe, this process 3 to 4 is taking place at constant pressure, that is P3 is equal to P4. So for this HF3 is equal to HF4. So if I write this, H3 is equal to HF3 plus X3HFG3 minus HF4. But this process is taking place at constant pressure. So if we refer the steam table, then at pressure P3, which is equal to P4, the value of HF will remain same. That is HF3 is equal to HF4. So this will be getting cancelled because HF4 is having minus sign, and which is equal to X3HFG3 is the formula to calculate the heat rejected. Now again we will move for the next process, that is process 4-1, which is the warming at constant volume. So if we observe, here is the hot well where the process 4-1 is taking place. So volume will remain constant, warming, that means we can say heat addition process, and due to heat addition process pressure increases, temperature will also getting increased, and due to heat addition process we know that entropy increases. Now due to here warming process, if we observe, the saturated water phase will remain same, that is the heat addition is known as the sensible heat, because the phase of this working substance remain constant. So we have to show all this process. So I will show here 4-1 process, that is straight vertical, and because volume will remain constant. Then here for the temperature entropy diagram, we have to show this increase in temperature along the saturated liquid line, because this phase of the working substance will remain same. So here will be H, that is 4.4, I will say here entropy S4. So its entropy is also getting increased because S1 is greater than S4. Now again main important point is that how to calculate the heat absorbed. So heat absorbed during this process. So again we have to take the difference in between these enthalpies, that is HF1 minus HF4. So I will write here heat absorbed is equal to HF1 minus HF4. Now again if we observe, HF1 is equal to HF2 because this 1-2 process is taking place at constant pressure. So I can write here HF2 minus HF4 is equal to HF3 because again here this process is taking place at constant pressure. So I can write here HF3. So heat absorbed we can use HF2 minus HF3. We will solve one problem. Steam is supplied at 10 bar and the exhaust takes place at 0.2 bar. Find Rankine efficiency with the help of steam table if the steam is initially 90% dry. Let us understand what is the given data. It is given that steam supplied at a pressure of 10 bar and exhaust at 0.2 bar. Now if we observe the different processes, then in this boiler saturated water is getting converted into steam. So here pressure of steam during the process 1 to 2 is given, that is 10 bar. So this process 1 to 2 is taking place at constant pressure. So we can say that P1 is equal to P2 is equal to 10 bar. And it exhausts at a pressure of 0.2 bar. So steam is getting exhausted during the process 3 to 4, that is in the condenser. So here we can say that the pressure at point 3 which is equal to pressure at point 4, because this is the constant pressure process. So it getting exhausted from this turbine, because in the turbine there is the decrease in pressure. So at point 3 pressure is 0.2 bar, but here process 3 to 4 is the constant pressure process. So we can say that P3 is equal to P4 is equal to 0.2 bar. Now it is also given that initially the dryness fraction of steam is 90%. So what is the meaning? So initially steam is at with 90% of dryness fraction. So initially that means when the saturated water is getting converted into steam, that is at point 2, dryness fraction is equal to 90%. So we can say that X2 is equal to 90%, and 90% that means 90 divided by 100, which is equal to 0.9. So we have to take here X2 value 0.9. and we have to find out what is the Rankine efficiency. Now if we observe the given data, there is incomplete evaporation because during the process 1 to 2, saturated water is not getting converted into saturated vapor or saturated steam, dry and saturated steam. So here the dryness fraction is given, that means this is the case of incomplete evaporation. And x2 is also given, that is equal to 0.9. Now we have to find out the Rankine efficiency. So what is the formula for Rankine efficiency? That is equal to H2 minus H3 divided by H2 minus HF3. Now what is this H2 and H3? So if we observe the condition of working substance at point 2 and at point 3, that is both are having wet steam. So we can say that H2, that is the enthalpy at point 2 is equal to H2, enthalpy at point 3 is equal to H3. So how we can define this H2 and H3? So we know that H2 is equal to HF2 plus X2 HFG2 and H3 is equal to HF3 plus X3 HFG3. Now this X2 is given, but X3, that is the dryness fraction at point 3, is unknown. So how to find out? So if we observe this point 2 and point 3, then these 2 points are having same entropy, that is S2 is equal to S3. So we can write here S2 is equal to S3. So how we can define this entropy S2? So again entropy S2, that is SF2 plus X2 SFG2 and S3 is equal to SF3 plus X3 SFG3. Now how to find out this value of SF and SFG at point 2? So this at point 2 we have to refer pressure P2, that is equal to 10 bar. So we will use here the steam table, that is the pressure table. In the first column pressure is given. Now the pressure is given, that is 10 bar. So in the first column we have to take here the 10 bar pressure and we will find out the value of SF. So here SF 2.138 given and SFG, that is 4.445 is given and X2 is known, that is 0.9. In the same way we will use the value of SF3 and SFG3. So at point 3 there is pressure P3. So P3 is equal to P4 is equal to 0.2 bar. So again at pressure 0.2 bar we will refer here the steam table. So here is 0.2. Again we will refer here SF value. So SF, that is SF3 0.832 and X3 we will write as it is because this is unknown, and SFG, that is 7.077. Now here only one term that is unknown. So we have to first solve this bracket, that is this multiplication. Then we will add this term and then we will take this 0.832 to the left hand side. So we have to subtract this and then we will divide the whole answer with 7.077. So X3 is equal to 0.749. So this is the dryness fraction at point 3. Now we can easily calculate the value of H2 and H3. So what is H2? That is we have to take HF and HFG at point 2. So that is at pressure P2, again that is for 10 bar we will find out the value of HF and HFG. So at 10 bar HF is 762.6 and HFG, that is 2013.6 and this X2 is known. So when we solve this, then we will get the answer 2574.84. Then in the same way now H3 is also known, so we can calculate this H3. So how to calculate this HF and HFG? So again at point 3 we have to refer pressure P3, that is 0.2 bar. So again for 0.2 bar HF and HFG, that is 251.5 plus 0.749, this is the value of X3 multiplied by HFG, that is 2358.4. So when we solve this we will get the H3 2017.94. Now we will move for the calculation of Rankine efficiency. So this H2 is known, H3 is known and HF3. So HF3 is also known because we have already taken here for the calculation 251.5. So when we put all this value, then we will get the answer 0.2396. But here efficiency is there, so we have to convert this into percentage. So we will multiply here with 100 and answer is 23.96%. So this is the answer.